In this video, we will see how mass and energy are equivalent to each other. We will then see how nuclear binding energy and mass defect are related to the formation of a nucleus. Afterwards, we will explore how the average binding energy per nucleon can be used to determine the stability of a nucleus. A consequence of Einstein's theory of special relativity was that particles at rest have an intrinsic energy. This energy can be calculated with the equation E equals mc squared, where m is the mass of the particle and c is the speed of light. We can see that the speed of light squared acts as the conversion factor between mass and energy. Moreover, if there is a change in energy to a system, this equation shows that there will be a corresponding change in mass and vice versa. The SI unit for mass is the kilogram, but this is a very large unit when talking about atomic particles. So instead, we use a smaller unit of mass called a unified atomic mass unit, denoted by U. This is defined as 1/12 of the mass of an isolated carbon-12 atom, and has a value of 1.661 times 10 to the power negative 27 kilograms. This is approximately equal to the rest mass of either a proton or a neutron. We can now use the mass-energy equivalence to calculate how much energy corresponds to a mass of 1 U. Substituting the relevant values shows 1 U is equal to 1.49 times 10 to the power negative 10 joules, and then we can convert this into electron volts using the following calculation. This value is often quoted in mega-electron volts. So we find our mass of 1 U is equivalent to 931.5 MeVs of energy. If the energy in the mass-energy equivalence is measured in MeVs, the mass will often be quoted in MeV per c squared, as this allows for easy conversions between mass and energy. From this, the units on the unified atomic mass unit is also written as 931.5 MeV per c squared as shown in the data booklet. Recall that protons and neutrons in a nucleus are held together by the strong nuclear force. To overcome the strong nuclear forces and completely separate a nucleus into its individual nucleons, work must be done. The total energy required to do this is called the nuclear binding energy. Alternatively, we can see nuclear binding energy as the energy that will be released when a nucleus is formed from individual nucleons. The more nucleons in a nucleus, the greater the total binding energy will be. But as we saw, energy and mass are different aspects of the same quantity from the mass-energy equivalence. In separating a nucleus into its constituent nucleons, the energy input is converted to mass and results in an increase in mass. So the total mass of the individual nucleons making up a nucleus is greater than the mass of that nucleus. This difference in mass is called a mass defect, and is the mass equivalent of binding energy. In nuclear physics, an important experimental quantity is the average binding energy per nucleon, and we can calculate this quantity by taking the total binding energy of the nucleus and dividing it by the total number of nucleons in that nucleus. Before seeing its importance, let's apply our current knowledge to the following example. Part 1 wants us to calculate the mass defect of an iron 56 nucleus. To do this, we begin by noting down the number of protons and neutrons in the nucleus. The mass defect is then calculated from the difference between the total mass of the nucleons and the mass of the iron 56 nucleus. The rest mass for a proton and a neutron can be found in the data booklet, so the total mass of nucleons is determined as follows. After subtracting the mass of the nucleus, we find that the mass defect is equal to 0.5285 U. To calculate the binding energy in part 2, we can use the equation E equals mc squared, since mass defect is the mass equivalent of binding energy. By noting that 1 U is equivalent to 931.5 MeV per c squared from the data booklet, we can convert the mass defect into these units, and then the c squared terms will cancel each other out. Completing this calculation then gives 492 MeVs for the binding energy of iron 56. Finally, in part 3, we note that there are 56 nucleons in iron 56. So the binding energy per nucleon is calculated from taking the 492 MeVs from part 2 and dividing this by 56, giving a value of 8.79 MeVs. The quantity binding energy per nucleon is used as an indicator to the stability of a nucleus. The following graph shows how the average binding energy per nucleon varies with nucleon number, and we can note down some of its features. The binding energy per nucleon increases steeply at low nucleon numbers, since the strong nuclear forces between nucleons will dominate. Moreover, there are peaks at helium-4, carbon-12, and oxygen-16, which shows the particularly high stability of these nuclei compared to their immediate neighbours. The graph reaches a peak of around 8.79 MeVs near iron 56 and nickel 62, which shows that these nuclides are the most energetically stable nuclei. The binding energy per nucleon then slowly decreases for large nucleon numbers. The binding energy per nucleon curve also gives an insight into which nuclei undergo nuclear fission and fusion. Nuclear fission is a reaction where a massive nucleus splits into two lighter nuclei. On the graph, a fission process can be represented by an arrow to the left. In such a reaction, energy is released because the resulting daughter nuclei will have a higher binding energy per nucleon than the original parent nucleus. Another way of thinking about this is that the energy required to pull the original nucleus apart is less than the total energy that is released when the two daughter nuclei form. So nuclei located to the right of the peak of the curve will become more stable by fission. For large nuclei, fission results in an overall decrease in mass and a release of energy. On the other hand, nuclear fusion is a reaction where two light nuclei are combined to form a more massive nucleus, and can be represented by an arrow to the right on the graph. In this scenario, energy is released because the fused nucleus will have a higher binding energy per nucleon than the lighter nuclei used to form it. Therefore, nuclei located to the left of the peak of the curve will become more stable by fusion. Like the fission of large nuclei, the overall mass will decrease when two light nuclei are fused together, and energy will be released. We will now provide a final summary of the key understandings from this video. We began by stating that particles at rest have an intrinsic energy, which can be calculated with the equation E=mc². We then saw that nuclear binding energy is the work required to separate a nucleus into its individual nucleons, or the energy released when the nucleus is formed from individual nucleons. The difference in mass between the nucleus and total nucleons is called the mass defect, and is the mass equivalent of binding energy. Finally, the average binding energy per nucleon can be calculated by dividing the total binding energy by the total number of nucleons. This quantity is used as an indicator to the stability of a nucleus, and we found that nuclei located to the right of the peak will become more stable by fission, while nuclei located to the left will become more stable by fusion. This now concludes our video on nuclear binding energy. Thank you for watching.